Hi, in this video we're going to be talking about the method of partial fraction decomposition to evaluate an integral. So a partial fraction decomposition takes a rational expression, that is a polynomial over a polynomial, and if we can't normally solve it, we can break it up into several expressions that we can integrate via normal means. Now this works even for rational functions that we can integrate. So let's start by actually looking at one that we can integrate and compare it side by side with the partial fraction method. So let's start with the integral of 2x minus 1 over x squared minus x minus 6. Now the usual method would be to just use a u substitution. And we can see that the top is the derivative of the bottom. So let's let u equal the bottom, then du is going to be the top. And when we make our u substitution, it's just the integral of du over u, which is just the natural log of the absolute value of u plus c, and then substituting u in for x squared minus x minus 6, we get the natural log of x squared minus x minus 6 plus c. Now let's look at the method of using partial fractions to solve this problem. So what we're going to do is we're going to write 2x minus 1 on top, but on the bottom, let's actually factor x squared minus x minus 6 into its two factors. So we get x minus 3 times x plus 2. So let's give ourselves a little bit more room and see what we can do. So now when we break this up, what we're doing is we're going to take 2x minus 1 over x minus 3 times x plus 2, and we're going to break it up into two fractions. So we're going to break it up into something over x minus 3 plus something over x plus 2. And the question is, what are those two things going to be in the numerator? Well, if we look at the denominator, we know that the denominator is a linear function. So if the top were also linear or above, say like x plus 7, we could divide using long division to simplify this even more. So by having these particular factors on the bottom, we're going to want something that is of a degree less than what we have in the bottom. Okay, so anything less than linear is going to be a constant. So we're going to have a constant over x minus 3 and a constant over x plus 2. So let's call them a and b respectively. Next, we're actually just going to solve what a and b are. And to do that, we're going to clear the denominator. So we're going to multiply the left-hand side and the right-hand side by the common denominator, which is x minus 3 times x plus 2. And on the left-hand side, they clear out. On the right-hand side, we're going to have to distribute. So the left-hand side, we have 2x minus 1 because the factors that we multiplied by cancel out the denominator. Now on the right-hand side, the x minus 3 and x plus 2, we're going to distribute that. And the x minus 3s are going to cancel on the a, and the x plus 2s are going to cancel on the b. So we're left with a times x plus 2, the remaining factor, plus b times x minus 3, the other remaining factor. So now let's go ahead and distribute the a and b. So we get ax plus 2a plus bx minus 3b. After that, let's go ahead and gather our x's and our constant terms. So for our x's, we have a plus b, and we'll multiply that by x, plus 2a minus 3b, and those are our constants. And remember, this is equal to 2x minus 1. So to figure out what a and b are, let's go ahead and set our coefficients equal to each other. This is called equating coefficients. So we're going to set a plus b equal to 2. We're setting our x's equal to each other. and we're going to set 2a minus 3b equal to -1. We're going to set our constants equal to each other. So now we have a system of equations. We have 2 equations and 2 unknowns. So we can solve for a and we can solve for b, and that solution, if it exists, is unique. So let's go ahead and use substitution. We can solve this any way we'd like. You could make a matrix if you'd like and row reduce, but I'm just going to say a is equal to 2 minus b and plug that into our second equation, solve for b, and then reverse substitute to find out what a is. So a is 2 minus b, which means that 2a minus 3b is 4 minus 2b minus 3b, and that's equal to -1. And then going through the steps, baby algebra, solving for b, we get 1, and then a is going to be 2 minus 1, or 1. So now let's bring it all the way back to the integral and rewrite it with our partial fraction decomposition. So this whole integral is equal to 1 over x minus 3 plus 1 over x plus 2. And we can break that up into 2 separate integrals, and we get the log of the absolute value of x minus 3 plus the log of the absolute value of x plus 2 plus c. Now let's go ahead and compare that to what we had doing it the usual way. And at first they don't look similar, but remember that if we add the logs, we actually multiply if we bring it all together under 1 log. So this is the same as the log of x minus 3 times x plus 2, which when we multiply it out, we get the left side doing it the usual way. So it is a valid method and they are equal. Okay, so once we factor things out, we can determine what the fraction is going to look like based on what the factors are. So if the denominator has just a linear term by itself, we can, as we've already seen, just write it as a constant over the linear term. Now if the linear term is repeated n times, say, we have ax plus b to the n, what we're going to do is we're just going to have a constant over ax plus b. We'll call that a1. And then another constant, we'll call that a2 over ax plus b squared, a3 over ax plus b cubed, and an over ax plus b to the n. So it's just a constant over each power of it until we get to the last one. Now, if we have a quadratic, we said that it has to be of a degree lower than it. So what we're going to do is we're just going to have a linear term over our quadratic. Now, the important part is that this quadratic, we're just going to say it's irreducible. It doesn't necessarily have to be irreducible, but it's not going to be the simplest possible decomposition that we can work with. So we're just going to have that extra requirement that it's irreducible. And if we have this quadratic plus bx plus c to the nth power, we do the same thing that we did with the linear power, but we just have a1x plus b1 over ax squared plus bx plus c plus, say, a2 plus b2 over ax squared plus bx plus c squared, and we continue that where we'll have an plus b, or anx, my apologies, this should be a2x plus b2, and this should be anx plus bn over ax squared plus bx plus c to the nth power. And we can continue this process. So let's just do one more example. If I have ax cubed plus bx squared plus cx plus d, so I have a cubic, well, it should be 1 degree less. So this should be ax squared plus bx plus c over our cubic. So ax cubed plus bx squared plus cx plus d. And we can just continue this process. But just note that for best results, what we want to do is make sure that our polynomials in the denominator are in fact irreducible. So let's go ahead and look at one more example. 3x plus 11 over x squared minus x minus 6. Now, we know that x squared minus x minus 6 breaks down into x minus 3 times x plus 2. Another important thing to note is while we had the same denominator, we had a different numerator. And with that numerator, we could have just done a u substitution. But with 3x plus 11, we can't quite do a u substitution to just get a simple natural log. So let's go ahead and break this up. So we'll have 3x plus 11 over x minus 3, x plus 2, and it's going to be a over x minus 3 plus some constant b over x plus 2. And now we just clear the denominators by multiplying everything by x minus 3 times x plus 2. And we get 3x plus 11 is equal to a x plus 2 plus b x minus 3. And by distributing the a's and the b's and combining our x's and our constant terms together, we get a plus b x plus 2a minus 3b. And that's going to be equal to 3x plus 11. Now we can just set everything equal to each other by equating coefficients. So a plus b has to be 3. 2a minus 3b has to be equal to 11. And when we solve this system of equations, I'll leave it to you to figure it out. But we're going to get 4 over x minus 3. That is, a is equal to 4. And b is going to be equal to negative 1. So 4 over x minus 3 minus 1 over x plus 2. And we just have to integrate this now. And now it becomes really simple because each of these are simple log rules. So we get 4 log x minus 3 minus the log of x plus 2 plus c. And if you're a real go-getter, we can rewrite this as the log of x minus 3 to the 4th over x plus 2. Make sure you have your absolute values. For our next example, let's look at this integral, the integral of x squared minus 29x plus 5 over x minus 4 squared times x squared plus 3. So to first start this, what we're going to have to do is split up the bottom. So let's just rewrite the original problem here, at least the inside of the integral. So x minus 4 squared times x squared plus 3. And remember, we have a linear term that is squared. So we write it first, and then we add x minus 4 squared. And if it were x minus 4 cubed, we'd write another term with x minus 4 cubed. So we're just writing the denominator of the fractions with each of the factors. Now, this is a linear term, so it's just going to be a constant on top. The second is a repetition of a linear term, so we're just going to write another constant on top. And the third one is an irreducible quadratic, or it has order 2. So what we're going to do is we're going to write a linear term on top. Now, we have to clear the fraction, so we're going to multiply everything by the least common denominator. And the least common denominator is going to be, and it's always going to be, the thing that we started with. So it's going to be x minus 4 squared times x squared plus 3. So on the left-hand side, multiplying, we're just going to multiply this by the LCD. We're going to multiply this by the LCD. So we get x squared minus 29 plus 5 on the left-hand side. And on the right-hand side, we get a. Now, one of the x minus 4's cancel, so we still have 1 left. And we're going to multiply that by x squared plus 3 as well, because it never canceled. And then we're going to add b. Now, both of the x minus 4's cancel, times x squared plus 3, plus cx plus d, times the x squared plus 3's cancel, so we have x minus 4 squared left over. Now, we could go through the process of multiplying it all out, seeing what our x cubed terms are, x squared terms are, and so on, and then equate coefficients. But there is a small trick that we can use. We know that there are certain values of x that'll make these things cancel out. So let's go ahead and choose specific values of x such that we can go ahead and eliminate some of the constants so we can determine what the other ones are. And then, if necessary, we can go through with what we already have and figure out the rest. So let's let x equal 4. If x is equal to 4, we have a times 0 times 16 plus 3, and then we have b times 16 plus 3, which is 19, and we have cx plus d, so we have 4c plus d times 0 squared. So everything cancels out except for the b, so we have 19b on this side. So now let's plug 4 in to the left-hand side and see what we get. So we have 16 minus 29 times 4. And let's go ahead and do that real quick. So 4 times 9 is 36. 4 times 2 is 8. So it's 116 plus 5. 16 minus 116 is negative 100. Plus 5 is negative 19. So R is negative 95. So B is negative 95. Now 95 over 19 is actually 5. So B is negative 5. Now let's go ahead and choose another value of x. So let's keep a tally over here. We don't know what a is just yet. We know that b is now negative 5. C, we don't know what that is yet, and we don't know what d is yet. But let's go ahead and pick another value. So we want x cubed plus 3 to go away. Unfortunately, we don't really have much of another choice here. So let's plug in -5 and see what we can get. So we have x squared minus 29x plus 5 is equal to a times x minus 4, x cubed, x squared plus 3, times plus b, which is -5, so plus -5 times x squared plus 3, and then plus cx plus d times x minus 4 squared. Okay, now let's go ahead and distribute that -5. So we have a x minus 4, x squared plus 3, minus 5x squared minus 15, plus cx plus d times x minus 4 squared. So we can move that -5x squared and that -15 over, and when we do that, we get 6x squared minus 29x plus 20. And that's going to be equal to a times x minus 4, x squared plus 3, plus cx plus d times x minus 4 squared. Now let's multiply out x minus 4 and x squared plus 3. So that's going to be x cubed minus 4x squared plus 3x minus 12. And then we have cx plus d times x squared minus 8x plus 16. Multiplying this out even more, we see that cx plus d times x squared minus 8x plus 16 is cx cubed minus 8cx squared plus 16cx plus, distributing the d, dx squared minus 8dx plus 16d. And so when we do this all out, we get ax cubed minus 4ax squared plus 3ax minus 12a. And then we have cx cubed minus 8cx squared plus 16cx. And then we also have dx squared minus 8dx plus 16d. And as you can see, the way I've written it out, we actually have our x cubed column, we have an x squared column, we have an x column, and we have a constant column, which we could call x to the 0. So now all we have to do is set these things equal to 6x squared minus 29x plus 20. So we know now that a plus c is equal to 0 because the left-hand side has no x cubed terms. We know that negative 4a minus 8c plus d is equal to our x squared term, which is 6. And we have 3a plus 16c minus 8d is equal to our x term, our x term, which is negative 29. And we have negative 12a plus 16d is equal to our constant term, which is 20. So now that we have all of this information, we can go ahead and solve this for a, c, and d. which is really nice because we have 4 equations with 3 unknowns, so we can actually solve this in a much more versatile way than having the. So the first equation, let's label them 1, 2, 3, and 4. The first equation tells us that A is equal to negative C. So this is really useful for us, especially considering how we can plug it into 4 now. And 4 now tells us that 12C plus 16D is equal to 20. And now we can solve for either one. Doesn't really matter. Let's go for C, so we can get everything in terms of C. So we can divide everything by 4, and we get 3C plus 4D equals 5. And so D is going to be equal to 5 minus 3C over 4. Now, we want something with a multiple of 4 times our D so we can get rid of that denominator. So let's plug this into equation 3. So 3A is the same as negative 3C. 16C is going to stay 16C. And negative 8 and 4 reduce. So we have negative 10. So it's negative 2 times 5 minus 3C plus 6C is going to be equal to negative 29. We can add that 10 over, and we get negative 19. And 16 plus 6 minus 3 is the same as 16 plus 3, which is 19. So we have 19C equals negative 19. So C is equal to 19. So let's go back up and fill C in here. C is negative 1, right? Because dividing both sides by 19 gives us negative 1. And this tells us what A is. A is negative C, which is negative 1. So that tells us that A is 1. And D is 5 minus 3 times negative 1 over 4. So that's going to be 8 over 4, or just 2. So let's go ahead and fill that in our tally, where A is 1 and D is 2. So let's go ahead and copy our box here. And we'll move it down here. And let's go ahead and get our original fractions. So we'll get this thing here. And we'll move that down as well. And now all we're going to do is replace A, B, C, and D in the appropriate ones. So we have 1 over x minus 4 minus 5 over x minus 4 squared plus negative x plus 2 over x squared plus 3. And that is going to be the integral of dx. And just as a reminder, our original function was x squared minus 29x plus 15 over x minus 4 squared times x squared plus 3. So these are actually equal to each other because we broke it down by partial fractions. So now we're just solving the right-hand side, and that'll give us the integral of the left-hand side. So when we do this, we have a u substitution here, where u is x minus 4, and du is dx. So here we just have the natural log of the absolute value of x minus 4. Now let's look at what happens when we let u equal x minus 4 here. Du is going to be dx. So we're going to have minus 5 on the outside of our integral, and it's going to be negative 5, zoom in here, integral of du over u squared. So remember, this is u to the negative 1, right? Or u to the negative 2. And when we integrate that, that's going to be u to the negative 1 over negative 1. So this changes this to plus 5 over x minus 4. Now the next one is a little tricky, so let's go ahead and do that on the side and then bring it back. So we're looking at negative the integral of x minus 2 over x squared plus 3. Let's go ahead and break this up into two separate integrals. So we can break this up into negative integral of x over x squared plus 3 plus the integral of 2 over x squared plus 3 with a dx on everything. So this one, we can just let u equal x squared plus 3. Du is going to be 2x dx. So we're going to put a 2 in here and balance it out with a 1/2. So this turns into negative 1/2 the integral of du over u. So bringing it back here, we have minus 1/2 the log of the absolute value of x squared plus 3. We technically don't need the absolute value for this particular one because x squared plus 3 is always positive, but it's always good practice to put absolute values when we evaluate an integral. This one, 2 over x squared plus 3, we can break this down into, well, let's put that 2 on the outside, and it's going to be dx over x squared plus 3. Now this is of the form x squared plus a squared, where a is equal to the square root of 3. So remember that if we have the integral of dx over x squared plus a squared, that's 1 over a arctan of x over a. So this is going to be 2 over the square root of 3 arctangent of x over the square root of 3, and when we bring it over, we can just go ahead and rationalize the denominator. And let's go ahead and slide all of this over because we don't really need it anymore, and we just need more room to write our final integral. So plus the square root of 3 over 3 arctangent of x over the square root of 3 plus c. And that is our final solution to this integral. And while it seems really long, really tedious, and really nasty, it is the best tool that we have to evaluate this integral thus far. Now, a final note is, what if we have some function, some linear function, say x minus 3 over x squared dx? Well, we can break this up into 1 over x minus 3 over x squared and integrate that, and we get the log of x plus 3 over x plus c. We could also use partial fraction decomposition. So we have x minus 3 over x squared. This is a repeated linear term. It's a quadratic, but we can also think of it as a repeated linear term. So we would have a over x plus b over x squared. And when we do this, we get ax plus b is equal to x minus 3. So a is equal to 1, b is equal to 3. And when we break it up, we get 1 over x minus, well, that's negative 3 minus 3 over x squared. And it's just a long way of doing the shortcut of just dividing.